Good morning student, myself Nayan Kumar Das, and today we are going to discuss about a very important topic of chemical bonding, that is hybridization. Before directly diving into the concept of hybridization, let's first understand or have some basic idea regarding VBT. VBT stands for valence bond theory. And it says that bond formation occurs with unpaired electrons. To explain this statement, I have taken the example of methane. We know that in case of the carbon, it has the electron configuration of 1s2, 2s2, 2p2. Let me write the downstream electronic configuration of it, which can be written as here you can see that in the 2s orbital there is a presence of two electrons which are paired. But in case of the 2p orbital, the two electrons are unpaired. So according to BBT, the bond formation occurs with unpaired electrons, right? So here there is a presence of only two unpaired electrons. So the methane should only form two CH bonds. But experimentally, what we have seen that the methane has total of 4 CH bonds, right students? And remember one thing, it is very important. The 4 CH bonds, all of them are identical, all of them have same bond energy, and all of them have same bond length. So what does the carbon do in this case? With the help of only the downstream electronic configuration, we cannot explain how it is forming 4 bonds. That is why the carbon undergoes excitation. What does that mean? That means that the 2s orbital, first of all, it undergoes excitation where it was present at ground state, then it goes to the excited state by promoting one of the electron from the 2s orbital to the vacant 2p orbital. This is called as the first excitation state. That can be written as like this: first excited state. Now we are having total 4 unpaired electron, but still there is a problem. The same, that is S has a spherical structure and P has a double orbital structure, right? So both of them are having different structures as well as both of them have different energies. So when the bonding occurs between the S and the P orbital, the next bond that is going to form is not going to be identical, not going to have the same bond energy, and not going to have the same bond density. To solve this concept, we introduce the concept of the hybridization. Hybridization. Let's now talk about hybridization. Hybridization is simply the intermixing of atomic orbitals of same or nearly same energy forming new orbital of same energy. Let me explain this statement. Here first there is an intermixing. So what is going to happen is in the first excited state here is the presence of 2s orbital and the 2p orbital. Both of them are going to intermix with each other. And remember that they are intermixing because their energy is nearly same. Nearly same. Not exactly same but nearly same. Okay. So after the intermixing, they will give 4 new orbitals. Remember, 1 2s orbital is mixing, 3 2p orbital is mixing. That results in the formation of giving us a new 4 hybrid orbital. Okay, that is sp3. First let me write sp3, sp3, sp3 and sp. Okay. So now we are having 4 sp3 orbitals. So you can take it as an example, students, that when in my one hand I have chocolate syrup and in my other hand I have vanilla ice cream. So when I am eating it differently, it is going to taste different, right? But when I'm mixing them together, that they will give me a rich flavor. Similar thing happen in case of the bonding. When one s orbital and 3 2p orbital combine together, they will give us a better bonding orbital. Remember, better bonding orbital. That is, so as you can see that I have drawn the structure here. This orbital of the carbon is now the sp3. This is also sp3 and this is also sp3 and this one is also sp3. So the 4 sp3 orbital now forms bond with the 1s orbital of the hydrogen. That results in the formation of 4 CH bond. This is 1s orbital of hydrogen. Okay. One very important thing to remember that all of this orbital, they do have the electron density in them, right? So they will try to repel themselves such that they will try to have a perfect shape where the repulsion is minimum. So after minimizing the repulsion, they are going to achieve a geometry that is called as the tetrahedron. Before moving forward, we must need to know 2 important points. Okay, that is, the first one is the number of the atomic orbital taking part in hybridization is equal to the number of the new orbitals formed. I will explain it a little bit later. And the next thing is that this is the structure of the hybrid orbital, which consists of a large lobe and also a smaller lobe. The smaller lobe has less electron density. That is why most of the time it ignores it. But the larger lobe, it has more electron density and it primarily acts as a bonding region. This larger lobe, this acts as a bonding region. So as we are familiar with the term hybridization, let's now understand the types of hybridization. So I have written orbitals. When one s orbital intermix with one p orbital, they will give us 2 new hybrid orbitals, that is sp and sp. It is having a geometry of linear with the angle of 180 degree. Some example of it are Bf2, BCl2, etc. Similarly, when one s orbital intermix with 2p orbital, that will give us 3 new hybrid orbital with a geometry of trigonal planar. That is, with having a bond angle of 120 degree. Some example of it are BCl3, Bl3, etc. Now when one s orbital intermix with 3p orbital, that will give us 4 new orbital, that is 4 sp3 orbitals. It is having a geometry of tetrahedral. Example of it are like CH4, water, that is H2O, NH3, and etc. Similarly, when we intermix one s orbital with 3p orbital and 1d orbital together, they will give us 5 new hybrid orbital, that is sp3d orbital, with a geometry of trigonal pi pyramid. Here, these 3 orbitals are present in the same plane and these 2 are are, this one is present above and this one is present below the plane. This is diagonal bipiramidal. For example, like PCl5. At last, when one s orbital intermix with 3p orbital and 2d orbitals. Okay, this will give us 6 new hybrid orbital, that is sp3d2, and it gives us the geometry of octahedral. Here, these 4 orbitals are present in the same plane, while these 2 are exactly like the above. One is present at the above one and the one is present at the below. This is the octahedral structure. Example, SF6. Now we will learn about the steric number. With the help of the steric number, we will be able to find the geometry as well as the hybridization of any molecule. But let's first go through its definition. The definition says that it is the number of orbitals that are involved in hybridization. For example, when there is only one orbital is involved, there is no hybridization at all. Similarly, when 2 orbitals involved, the geometry will be linear and it will give us a sp hybridization. When 3 orbitals involved, this will give us parallel geometry and sp2 is the hybridization. Similarly, when the 6 orbital involved, it will give us octahedral geometry and sp3d2 hybridization. Now, I will give you a simple trick. It is a very important trick through which we can easily will be able to find the hybridization as well as the geometry of any of the molecule. Now, we are going to learn a very important short trick which is going to be very much helpful to your students, through which you can easily able to find the hybridization of any molecule. This formula goes by Z, which is the steric number is equals to half times multiplied with number of the valence electron on the central atom. Remember, we have to take the valence electron of the central atom only, minus the positive charge. If the molecule carries any positive charge, then we have to minus it, and then add the negative charge. Okay, if any of the negative charge is present on the molecule, then we have to add it. At last, we have to add the number of the monovalent atom. If there is any presence of the monovalent atom like hydrogen, fluorine, bromine, etc. Okay, so let me just take some few examples. BF3. This was asked in NEET 2024. For example, in case of the BF3, half times boron has the number of the valence electron is equal to 3. So 3 minus any positive charge. As you can see, there is a presence of no positive charge, plus any negative charge. There is no presence of the negative charge over here also, plus number of the monovalent atom. Yes, it definitely has many 3 monovalent atom, that is fluorine. So 3 plus 3, that will give us 3. So it is going to have the hybridization of sp2, right? Similarly, for PCl5, it was also one question for NEET 2024. Okay, so Z equals half times into number of the valence electron of the central atom. Here, first plus is the central atom, so it is having 5 valence electrons, right? As it comes below nitrogen. Minus any positive charge. There is no positive charge. So minus 0 plus any negative charge. There is also no negative charge. Plus 0 plus if there is presence of any monovalent atom. Here definitely it has 5 Cl atoms which are monovalent. So 5. That is 10 divided by 2. That is going to give us 5. So Sp3d. Okay. Now the last example, NO3 minus. For that Z equals half times multiplied with number of the valence electron on the central atom. Here the central atom is nitrogen. Okay. So nitrogen has 5 valence electrons. Minus if there is presence of any positive charge. It does not carry any positive charge. So minus 0 plus if it carry any negative charge. So yes, it definitely has one negative charge over here, so plus 1. Plus if there is presence of the number of the monovalent atom, if there is any monovalent atom. No, there is no monovalent atom, here only the oxygen is present, which is not a monovalent atom. Okay, so 0. That is 5 plus 1, that is 6 divided by 2. That will give us 3 with the hybridization of Sp2. With this, we have concluded the topic of the hybridization, where we have learned that hybridization, how it is responsible for the geometry. We have learned the type of the hybridization. Along with that, we learned a very important super trick through which we can easily will be able to find any hybridization of any of the molecule. Thank you.